Okay, hey everyone. We are going to talk about Chapter 2, Bronsted-Lowry acids and bases. So, we've generally talked about an acid as a proton donor and a base as a proton acceptor in General Chemistry 1 and 2, and that's going to be no different right now. So to remind you what that means, if you have some kind of acid, like let's say HF, it would break down into H plus and F minus. And this would be called an acid because it's got an extra H. And this is everything that we're doing is dissolved in water up until now. But the process still is exactly the same. If it starts with an H, it's usually an acid. Okay? But now we've broadened our horizons so that not only if it starts with an H is it an acid, now if it contains an H, it's an acid. So anytime it has an H, it's an acid. So an acid is anything with a hydrogen in it, because that hydrogen can be given off in the right situation. Okay, a base needs to be able to accept that hydrogen, and in order to accept hydrogen, you need to have some electrons. So a base, a Bronsted-Lowry base, both of these are Bronsted-Lowry. We'll get to Lewis here in a little bit. A base would be anything that has a double bond, a triple bond, or a lone pair of electrons. So anything that has a double bond, triple bond, or a lone pair of electrons is going to be a Bronsted-Lowry base. Now don't forget, sometimes we don't draw, usually we don't draw the electrons in chemistry, so in organic. So for example, if you have come across a molecule that looks like this, you might not notice that it has electrons, but its electrons are right there, even if we don't draw them. So usually anything that has an O or an N or a negative sign are going to have a lone pair of electrons, even if we don't see it. Okay, so let's go and answer these problems. Problem 2.1a says, which compounds are acids? Well, an acid is anything with an H. That one has an H. That one has an H. That one does not have an H. Oh, not so bad, right? Which compounds are Bronsted-Lowry bases? That's something that has a double bond, triple bond, or a lone pair of electrons. And we said lone pair of electrons usually is indicated with an oxygen, nitrogen, or negative sign. So here, this is no double bond there. We cross that out, the ethane. Here, we got an oxygen and a negative sign. Anytime you have a negative sign, it's definitely a go. So this is a base right here. And then here we have a triple bond, so this is also a base. Next, it said classify each of these as acid, base, or both. Well, if it's an acid, it's got to have a hydrogen. So let's go through and see which one of these have hydrogens. All of them do. This one has a hydrogen, it's an acid. This one has a hydrogen, it's an acid. This one has a hydrogen, it's an acid. Then we look at the base. This one has an oxygen, meaning it's got these lone pairs on it. So this must be a base. This one has no double bonds, triple bonds, or lone pairs, so it is not a base. And this one has oxygen on it, so it's probably a base because it's got lone pairs. Now we're cooking with peanut oil. This question. Decide which compound is the acid and which is the base, and draw the products. Okay, now we get to the fun stuff. To remind you, a base takes on the acid and the acid gives off the H, or a base takes on the H and the acid gives off an H. So when we're looking at this compound right here, we're looking for the thing that has an H that looks like it's easy to give off. And hopefully you saw that, and if you didn't, after some practice, we'll see this better. I'm going to redraw this just because it's hard to see in this area. So we have a Cl to a Cl to a Cl to an O to an O, and I'm going to draw the line here to an H because even though it doesn't ask us to, we're going to do arrow pushing. And then over here we have O CH3. It did you the service of drawing all these and telling you it was negatively charged. The other thing we might recognize is that this has a negative charge. This is definitely a base. Right? Okay, so if this is the base and this is the acid, don't forget, an acid gives off the H and base takes it on. We're always going to start our arrow pushing from the electrons, and all we're going to do is say, okay, these electrons here, or you could even start from this negative sign if you wanted to and not draw the dots. But this arrow right there is going to grab that hydrogen. But it only grabs the hydrogen, not hydrogen's electrons. So hydrogen's electrons have to go on the thing that it came off of. And we'll practice this a lot today. Hydrogen's electrons have to go on the thing that it came off of. So this is going to be in equilibrium with what we get over here. I'm going to redraw this CCl thing, or this 3Cl thing. And now, instead of hydrogen, we now have an oxygen with all its lone pairs, and it now has a negative charge on it, because those two electrons right here and here went onto the oxygen. If you remember, the oxygen originally had 2 lone pairs on it, in case you're confused why there's now 3. And then this thing picked up the hydrogen. So what happens is these 2 electrons right here and here now have become a bond with a hydrogen. Okay, so what you get is an H, bond it to an O with dots, and then the CH3. Cool. All right, let's look at this next one. Again, the thing that's negative is most likely going to be the base. That's this one. It's a little h, and I don't know if you can see, but there's a negative sign on there. So this is the base, meaning this is the acid. So this right here, these electrons are going to come over and grab a hydrogen. Bases do the grabbing. And then these electrons, remember, from a hydrogen have to go on the thing that's next to it. So they're going on, in case you can't see it, they have to go on this carbon right here. And what you end up with is this thing. Bond it to this triple bond here. And remember that the electrons from this hydrogen went onto the carbon right here. They go onto the atom that it's next to. And we could just, even though we don't have a carbon right there, we can just draw the dots. We know that there should be a carbon right there. And that would make that carbon negatively charged. Its formal charge would be -1. Okay, in case you forget about formal charge, just real quick, formal charge is valence minus sticks minus dots. There are 4 valence electrons. There are 3 sticks touching it. There are 2 dots touching it, giving us a -1. But pretty much anytime you're adding electrons to something, you're going to be making it more negative. Okay, and what we have left over here, this hydrogen, remember those 2 dots, bond it with that hydrogen. And now we have an H2. Cool. So these would be our products. Okay. Now it says draw the products formed from the acid-base reaction of HCl. So all of these are going to react with HCl. I'm probably only going to do the first 2 in an effort to save time. Okay. Actually, I'll do A because they're very similar. I'll do, darn, A, B, and C, just to make sure. Okay, so we're reacting them with HCl, which we know is an acid, right? So you look at this, and you know this is an acid, therefore this must be a base. And we look at this base, and we know that there must therefore be lone pairs. And always the lone pair is going to grab a hydrogen. The electrons from where the hydrogen was attached will go onto the atom that was next to it, to begin with, that it was attached to. And what you get is this. We have our original, and now we've taken that oxygen, right, and we've added a hydrogen. When you add a hydrogen to it, you lose a charge. So it was neutral before, now it's positive. These 2 dots right here were the things that formed the bond with that hydrogen, and there were still 2 dots on this. but we don't need to draw them, especially if we put the formal charge. And then we'd be left with a Cl minus. To remind you what a Cl minus would be, that would be 8 dots around it. Okay, let's do this next one. Here we have this, and we are adding HCl to it. I should have done a better job. Let's do H line Cl so we can follow it. Anytime we have an oxygen, it's neutral here, so we know it's got the 2 lone pairs. These dots right here are going to grab a hold of that H. These electrons are going to go there. And we can redraw it. But we have to remember, anytime you take on an H, it gets more positive. Those 2 dots are still there. You can draw them or not. It doesn't matter. And now that it took the H and these electrons went onto the chlorine, which is now chloride. You also don't need to draw the dots there. Okay, last but not least, this nitrogen one. I wanted to do the nitrogen one because I think it's important. When we react it with HCl, remember on the previous page we said bases are double, triple, lone pair. An oxygen or N or a negative usually represent that you have a lone pair. And you would here, right? You have a nitrogen, it's got 3 bonds, which means it must be 2 dots on it. And those 2 dots are going to come out and try to grab that hydrogen because this is the base. And then every time you do that, the electrons that were bonding the hydrogen go onto the atom that it was bonded to. If you take on an H, what happens to the charge? Hopefully you remember, it goes more positive. So we have a positively charged nitrogen there now. And we've taken on an H. I didn't do a very good job, did I? We'll put the H down there. But you could put it up here, you could put it over there. Doesn't matter right now. And then what we have left is a Cl minus. Okay. On this one, you should get, just looking at it, you'll get this, okay, after you grab the HCl. Because that lone pair, look at me, I'm just doing it anyway. And you get that. All right, moving on. Acid strength. Oh man, y'all, I've struggled so much with this. Not the material, but the best way to teach it. Because I really hate having you memorize things, but it does make it much easier in the long run. So I'm going to teach both ways. We're going to learn exactly why stuff is the way it is, and we are also going to memorize these pKa's because they'll be very helpful for you later. All right, to remind you of a pKa, or even a Ka, if you have something like F, and it breaks down into H plus and F minus like we've done, our Ka for this, or K of anything, this would be a double arrow actually, our Ka is products over reactants, to remind you of Gen Chem. And you don't need to know this, by the way, for what we're going to do, but we multiply our products and we divide by our reactants. Now hopefully you agree, the stronger the acid, if it goes really far this way, it's going to be a stronger acid. If the reaction makes a lot of H plus and F minus, it's going to be a strong acid. And if it does that, then this side gets bigger. So these 2 numbers right here would be big. If those 2 numbers right there are big, then that means the Ka is also big. So a big Ka means we have a strong acid. pKa is a negative log of the Ka. It's just a much easier way to represent it. But for pKa, it's the opposite because you're taking the negative log of it. pKa is going to be the opposite. Where if you have a really small Ka, small pKa, it means you have a very strong acid. Okay. So you can look at the pKa's and immediately determine which acid's stronger based on it. So for example, this hydrogen right here bonded to any kind of alkane is going to be pretty crappy acid, as opposed to HCl, which we just did a bunch of work with. That's going to be a really good acid, very strong acid. And all that's cool. But here's where I'm doing you a disservice. What this means, if you have a really, really big Ka and it goes all the way this way and we make lots of this and this, the reason we make a lot of this and this isn't because the acid's good. It actually has nothing to do with the acid, which is why I get a little bit frustrated teaching this. This has nothing to do with how much is going to break off over here. The reason this is a strong acid is because once it breaks apart, the reason this is an acid is once it breaks apart, this is the conjugate base, right? And the conjugate base is stable if it's a strong acid. Let me give you an example. So we have, let's compare HF and HCl. HCl is a strong acid. HCl breaks apart into H plus and Cl minus. It does not go back this way. The reason it doesn't go back this way is because this is very stable. If it's very stable, it means it's a very weak base. And maybe you remember that already, that if you have a strong acid, its conjugate base is really weak. That'd be great if you did, because that will help. But this breaks apart, and this is a super stable thing. And because it's so stable, it means it's already happy. It doesn't need to go back in the opposite direction. Okay, but when we look at HF, I've been drawing it every time with a double arrow, where it breaks down to H plus and F minus. That's because this is a weak acid. If it's a weak acid, that means it's got a less stable base. So this F minus, much like your grade if it's an F minus, is not so happy. It wants to join with this and go the opposite direction as well. And so that's the difference between a strong acid and a weak acid. It's not anything to do with these. It has instead to do with, if we take the H off and look at just the Cl minus and the F minus, which one's going to be more stable. And that's our ultimate goal today, is to look at the conjugate bases of things and determine what's the most stable base. Okay, so memorizing these is good. Knowing the why is way better. Okay. So it says estimate the pKa for the following bonds. All you do, let me just rip this sucker off, is use our little table here that you'll have memorized, and you can estimate the pKa for these. For example, here we have an N to an H. So you look over here, you're like, where is there an N and an H? Right here. That's about a 38. So this is about a 38. Here you have an O to an H. Hey, you got an O to an H here. That's a 16. This is probably about 16. Same with this one, except actually, no, it's not the same as this one. This is a little bit different. It's this thing right here. They didn't draw it out, but I should for you. This is a methyl group, a CH3 to a C, double bonded to an O to an OH. This is called a carboxylic acid. And a carboxylic acid is pretty acidic, right? It's got a 4.8, meaning its conjugate base, see that whole thing is a carboxylic acid. It's exactly the same thing, carbon, double bonded O to an H. So what this means is that the conjugate base of a carboxylic acid is really happy being alone. All right, let's look at each of these. Here we have what appears to be an alkane. Right? There's just carbons, carbons, carbons. Suddenly there's a hydrogen that we're looking at. This would be 50, about 50 for an alkane. Here we have an alkene, a hydrogen attached to an alkene. Hydrogen attached to an alkene is going to be about 44. And then once again, the nitrogen is going to be about 38. So you're going to want to have those memorized. And here's why. You can quickly look and see which one's stronger and which one's not. So they look like a negative, but it's really meant to be an about sign. Okay. Which one's stronger of all of these? You can be like, boom, this is the strongest because it's the lowest number. Which one's strongest of these? You'd be like, boom, this would be the acidic hydrogen. If something had to be an acid in this molecule, it's going to be this one that's going to give off the H. Okay, so the bigger the number, or let me do this, the smaller the pKa, the more acidic it is, the more stable its conjugate base is. Right? If you can understand those concepts, you'll be better off. And if you didn't understand it, I suggest rewatching this one more time and really getting it. Okay, it says draw the products of each reaction and determine the direction of the equilibrium. Okay, we've already done some acid-base reactions, so this won't be horrible. But now we just have to use our pKa to determine which side it wants to go. So here, hopefully you agree, you have a negative, and a negative is like a dead giveaway that that's probably a base. Okay, so our negative is going to act as the base, and this will be our acid. Our base is going to grab a hydrogen. I don't know which one, but let's go ahead and grab that one. Poor sucker. And now it's grab that hydrogen, and now do you remember what happens to these electrons here? They go on the atom that it was next to. They're going to go right on that carbon. So then over here, we'll be left with an H to a C to an H, double bond it to a C. Okay, you no longer have a hydrogen because it's been taken, and it's been not replaced, but we have 2 electrons. When you add electrons to something, it becomes a negative charge. Okay. And now this H minus, grab that H, and it's just H2. Okay, so why does this matter? How are we going to use that to figure out the direction of the equilibrium? Well, let's go back to our little table. And we know that if you have an alkene like this, the H coming off of an alkene is 44. And we know that if you have NH2, it's 35. And to be very clear, the reason I chose those two is because they were both the acid. So here we knew this was an acid, it's giving off an H. Over here, if we went the opposite direction, I hope you agree, this would be the base, it's got the negative sign, and this would be the acid. So we're comparing these two acids. One's at 44 and one's at 35. Which one's stronger? Hopefully you agree this one is a lower number, so it's stronger. What makes a strong acid strong is that it wants to give off its H, right? So this is the stronger acid. So it wants to give off H, not keep it. If it wants to give off its H, it did that by going this direction. And that's why this would be the direction of that reaction. Okay. Moving on to the next one. Here we have CH4. With an OH minus. I don't know why I drew it like that. Why do you do that? This has a negative charge. All right, hopefully you agree. This is probably the base. Anytime it's a negative charge, it's like a dead giveaway that it's going to be the base, and this is the acid. That base is going to grab a hydrogen. Which one? I don't know. It doesn't matter. Let's take that one. And then those electrons have to go on the atom that it came off of. And then what you're going to get is this CH3 thing. Remember those electrons went on there, so we now have a lone pair, and it's a negative charge. And this OH minus grabbed that H, so it's now an HOH, aka water, right? It was a negative charge, and now it's gained a positive charge from the hydrogen. Okay, but that wasn't even the question. The question was, which direction does it go? So we indicated this was the acid and this was the base. Over here, hopefully you agree, this is now the base, it's conjugate base, and this is the acid. So we have to ask ourselves, which acid's stronger? Whichever one is stronger will want to give its H off in the opposite direction. So if you remember, alkane has a 50 pKa. And this is an acid. Water is a 15.7. Which one's a stronger acid? The 50 or the 15.7? Hopefully you agree this one. This is stronger. And because it's stronger, the reaction will go that way. It wants to give off its H and it'll go that way. Okay, now we're done with pKa for a minute, for a while, actually probably the rest of the lecture, and instead we're going to look at why the pKa is the way it is, which is the portion I much prefer. Okay, there are 4 factors that affect the acidity of HA, and every book will tell you something slightly different, but there are 4 main factors. There's the element effects, so which atom is H on? Okay, if H is on an oxygen versus a nitrogen versus a chlorine, it's going to be a different strength of acid. The inductive effects. Inductive effects means, are there any electronegative atoms there on the molecule? Resonance effects. Does it resonate? If it does, it'll be a stronger acid. And hybridization effects. We're just going to look at sp3, sp2, and sp and find out the differences. Okay. So here it says increasing electronegativity increases acidity. That's great. As we get more electronegative, we increase the acidity. And hopefully that already makes a little sense, but if it doesn't, let me walk you through this real quick. I mean, we have the pKa's, obviously, but that's not the point of this. If you remember, for cannot clean out fridge, which one of those things likes electrons the most? Hopefully you remember it's this. This one loves electrons. Okay, so bear with me because this is going to be the most important part. So if you're fast forwarding through the video, hopefully you see all these stars that I'm drawing right now to make you stop and go back and listen to this. Acid strength, again, and we've written it before, is based on base stability. In other words, how happy is the base? If the base is super happy, it will be a strong acid when you have an H on it. So here we're looking at CH, NH, OH, and FH. Why they? I don't know. Somebody's not teaching this. CH, NH, OH, and FH, okay? And we want to ensure that if we take off this hydrogen, the thing will be stable, because if it will be, it'll be a stronger acid. And again, yeah, I know you already know the answer, but here's why this is the answer. Let's take off the H of all of these. Let's say this is a C minus. Let's say this is an N minus. Let's say this is an O minus. And let's say this is an F minus. Which one of those is happier? Well, you know that this one loves electrons, right? If it loves electrons, then it has extra electrons in a negative, and this one is the happiest. Okay, so of all of these, this one's the happiest base. So when you take HF and you break it down into H plus and F minus, if this thing is happy, then it has no reason to go back this way. Some of it still does. It's not the super happiest thing, as we're about to learn, but it's kind of happy, okay? It's pretty darn happy. It's certainly happier than O is, it's happier than N is, and it's way happier than C is, okay? So because this is happy, this is going to be the stronger acid when you add an H. So HF is stronger. Okay. Now that's wonderful. But I'm about to make our lives a little less fun. Darn, I'm looking for a periodic table. I wonder if I got one. Woo. Yeah, somebody's final exam from last year. Got it. Okay, so that's great. But I got some news for you. That there's another thing to look at as well. So if you're going across a row, like this way, you're looking at electronegativity. So if we were comparing NH like we just did to FH, FH is more electronegative, and therefore this is stronger acid, because F is happier with electrons on it. But if you're comparing two things in a column, let's say OH and SH, so OH and SH, it's actually an opposite trend of what you'd expect, and we'll talk about why that is. You're looking at size. So in columns and rows, you compare electricity or electronegativity. In columns, you compare size. So the bigger the size, so the stronger acid it's going to be. The bigger the size, the stronger acid it's going to be. Let me give you a reason why. So if we have HF, HCl, HBr, and HI, and we're comparing these acids. On the periodic table, it goes F, Cl, Br, and I. As we go down the periodic table, this I gets really big. Okay, like the I it's huge. So if we were to like actually draw it to scale, it'd be like H to a little f. It would be H to a slightly bigger Cl. It would be H to a slightly bigger bromine. And it would be H to a bigger iodine. Cool. All right, so to take a step back, acid strength is based on base stability, or how happy the base is. If we take off an H from all of these, and we give it its little negative charge that it would have if it lost an H in an acid-base reaction, you want to look at which one's happier. This F is really small and it's carrying a huge charge with it. It's very tiny, it's got a huge charge. This I is huge, and its charge is not such a big deal. Remember, these are magnets, right? So this magnet right here is going to be seeking out something to find, because it's a really strong magnet. But this is not as strong of a magnet. Imagine if anybody ever have a refrigerator where you go to stick a magnet to. I don't know why I'm drawing a refrigerator, but whatever. You go to stick a magnet on the refrigerator and it goes, it just falls down. That's because the amount of charge per area in your magnet is not big enough. It's just falls down. It's not interested in reacting. And that's what happens with this I-. It's already happy, and it has no reason to hold on to that H. So if you put HI in water versus HF, HF will break apart into H plus and F minus. but it also goes back because F is still not super happy, right? It's still got a really strong magnet. It's still grabbing a hold of this hydrogen and going back this way. But HI, because it's so big, will break apart into H plus and I minus. And this I minus is the weakest magnet in the world. It's not interested at all in grabbing a hold of that hydrogen. It's super duper weak. And because it's super duper weak, this is going to be a very stable base. If that's a stable base, then that means this must have been a very strong acid. Okay. All right, so given that, let's see if we can figure this out. Which hydrogen in each molecule is the most acidic? Okay, so here we have carbons, 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 oxygens, right? There's a bunch of hydrogens over here. You have an oxygen. You know that oxygen's more electronegative because oxygen's more electronegative, and you're comparing carbons and oxygen, that you're in the same row. So when you're comparing things, a hydrogen attached to things in the same row, carbon and oxygen, that you're looking at electronegativity. This is more electronegative, and therefore this would be more stable as a base. And therefore this would be a stronger acid. So that right there is going to be the stronger H. Then we look at this, we got an O and an N, O and an N, same row. Same row, we're also looking at electronegativity. You could have already memorized that this is a 38 pKa and this is a 16 pKa, and you can be like, I know this one's going to be stronger, right? But even if you didn't, you know now that oxygen is happier on its own with a negative charge than nitrogen is, and that's why this is more acidic, or the stronger acid. Okay, so that was probably the funkiest thing we're going to go through. Again, I recommend doing it again if you need to. But we are going to move on to inductive effects, which comes generally pretty naturally to most people. So for inductive effects, I'm going to explain it in a way I wasn't planning on until right now. So this is a stronger acid than this one because this has a bunch of fluorines on it. Fluorines are electronegative, chlorines are electronegative, bromines are electronegative. Pretty much any halide that you have added to this is going to pull electrons this way. So imagine, remember this oxygen right here is bound to that hydrogen with that little bond right there. And that's 2 electrons there and there. And those electrons are being shared kind of between the oxygen and the hydrogen, right? But we know that those two aren't shared equally and that they move around, and there's something called electron density where they hover more toward the oxygen. Now imagine if you have these fluorines calling those electrons, come this way, come this way. They want those electrons to go this way, right? Super strong dipole that way. If they're pulling those electrons this way, then they're pulling those electrons closer toward the oxygen, right? What happens to that hydrogen? They're even pulling it closer to this carbon here when we talk about conjugate bases, but it's pulling it all this way. And this hydrogen is like, meh. It doesn't have any desire to stick around because this is already way stable. The base is already way stable without the hydrogen there, okay? And so therefore, this will be more acidic. It's more readily able to give off its H. So the thought is actually pretty straightforward. If you have more electronegative stuff closer to the H, it will become stronger. Okay, I just realized how gross my nails are, you guys. It's because I was drawing on the blackboard. Sorry, my nails aren't just that gross, it's dry erase marker. Anyway, so going this way. Here we have a chlorine and a fluorine. What's more electronegative? Hopefully you agree, it's the fluorine. And because Fluorine is more electronegative. It pulls a little more. So this dipole goes a little bit bigger than this one, right? You have a bigger arrow going this way. We're pulling those electrons away from this oxygen-hydrogen bond, and because of that, this will be the stronger one. It's more readily gives off its H. All right, and then we look at these two. More electronegative stuff closer to the acidic H. So here we have acidic H's here and here, but here, even though we have 2 chlorines on both of them, these two are closer, so they have more of an impact, more of an effect of what they can do, as opposed to this, which would be a smaller dipole. And because of that, this would be the stronger acid. Okay. Now we're cooking with peanut oil. Resonance effects. Yeah, yeah. It's one of my faves. Okay, so if a molecule can resonate, and by molecule I should say, let's change this. If the conjugate base can resonate, that means it's more stable, and that means it came from a strong acid. Okay, so if the conjugate base can resonate, that means it's more stable. It came from a strong, therefore the acid was strong. So what we do, we look at these things, much like we did in the previous example, we take the H off. Okay, we pretend the H went away, that the electrons went onto the thing next to it, like that, and we compare the two. So in this one, if we take that H off, we have this. Right? And in this one, we have this acetylate. Okay, which one of those two can resonate? Hopefully you agree this one can't do diddly smack, because just to remind you, in case, because I know we haven't spent a lot of time on resonance. Lone pair of electrons, if a lone pair of electron came down here, then that carbon would have 5 bonds, and that can't happen. So this one doesn't resonate. However, this one, if these electrons pop down there, then it can cause these electrons to pop up here, because otherwise there would be 5 bonds. We can't have that. And this resonates. And we'd get this. And anything that can resonate is more stable. So this has no resonance. It's got a less stable conjugate base. And that makes it a weaker acid. This one has resonance. Because of that, it has a more stable conjugate base. And therefore, it's a stronger acid. And that's why any of those carboxylic acid things that we were talking about, they're going to usually be pretty strong acids. We said they were pKa 4.8. All right. Last but not least, hybridization and S character. So it says S character, increasing percent S character increases stability. It's increasing the stability of the conjugate base, right? So these are all conjugate bases that it's showing. So it took the H off and it's like, look at this, look at the stability. The reason for that, if you remember, and hopefully this makes a lot of intuitive sense, in class, if you have a single bond, it's short. Or, sorry, it's long. It's like when we were holding hands in class, like just one, and then when you come together, it's medium, and then when you put your foot out, it's short. If you have something squashed and close, it's going to be more stable than something spread out and long and lanky. Okay, so this one is short, and therefore it's going to be more stable. It's really pretty much that simple. Okay, and because of that, the single bonded ethane here has a high pKa. This is a weak, just to remind you. And this is stronger over here. And again, it has nothing to do with the acids itself. It's if you take off an acid, take off that H, put a negative sign in its place. This one is shorter and more compact, and therefore it's going to be more stable. Okay, let's put it all together. See how you guys are feeling. So if we have to rank these, without knowing any of the numbers themselves, just using what we know, remember the first thing we'd want to do is think about the stability of the conjugate base. So if it's a stable conjugate base, it'll be a stronger acid. So if we took off the H there, made that a negative, we took off the H there, made it a negative, and we took off one of those H's there, made that a negative, which one's the most stable? Well, first, maybe you can go between these two, because they're very similar, right? And we know that atomic effects make a difference. Do you remember where the negative's more stable? Hopefully you remember the negative is more stable on the more electronegative thing. And oxygen is more electronegative than nitrogen. Okay, so of these, this one so far is winning. But now let's look at this. Do you remember inductive effects? This chlorine pulls the electron density away, and it actually helps stabilize all these bonds in here because it pulls the electron density this way. So that one's that, and this one doesn't have that dipole. Because of that, this one is going to end up being the most stable. So this is the most stable. This is the least stable. And this is the middle. But if you remember, stability has to do with acid strength. If it's really stable, if the base is really stable, that means it came from a strong acid. So this would be the strongest acid. And this one over here would be the weakest acid. All right. Well, I didn't want to do this part, but we'll do it. We're here. Let's finish it. Get some water. So, we're going to talk about Lewis acids and bases. We just talked about Bronsted-Lowry acids and bases. And Bronsted-Lowry acids and bases have the H, and it's moving around. It's a proton donor, proton acceptor. Here, a Lewis acid is an electron pair acceptor, and Lewis base is an electron pair donor. The good thing is a Lewis base will look very much like a regular base. So it's got a lone pair, or it's got a double bond, or it's got a triple bond. If you remember, those were the requirements for a base in the past. A Lewis acid is going to be an electron pair acceptor. What that means is it's going to have some kind of, generally, some kind of partial positive or electron deficient atom in it. Some kind of partial positive or an electron deficient atom. These tend to be the two main things that you'll see, BF3 and AlC3. So AlCl3. Okay. The reason for that is we'll look down at this BF3 right here. Here's a boron. And it's got 4 fluorines. And we know fluorines are super electronegative, right? So this is pulling that, this is pulling that, this is pulling that. And if all these are pulling electrons away from this poor boron, what's happening to the boron? Hopefully you agree it's got a partial positive on it, right? These all have partial negatives. And this poor boron is deficient. It's like, hey, I'm just positive over here. Good old optimistic boron. And so what happens is, remember, everything's magnets. This is a positive charge, and over here, oxygen over here has a partial negative, right? So it's got electrons right here, and those electrons can seek out like a little missile, boom, and grab that boron. Now, essentially, with a Lewis acid, this kind of acts like a hydrogen. The whole thing acts like a hydrogen. So in the past, we've seen it grab just one single hydrogen. Here, it's going to grab the whole thing and attach to it. So when it grabs this, these two dots right here add onto the boron. Boron was a neutral charge. Remember, boron, if you did valence minus 6 minus dots, it was 3 minus 3 minus 0 equals 0. It has a zero formal charge. But when you add an extra bond to it, here, it takes on now a negative because there's an extra electron that wasn't there before. And oxygen here has given away an electron to pair with boron, and so it takes on a positive charge. Okay, here, we know, hopefully this is a negative. We're like, that's definitely a base, right? And this has the positive charge. We said anytime we have something positive or a deficient electron deficient atom, it's going to be an acid. So this is the acid, and these electrons are like a little missile. We always go from the electrons to the positive thing, and that's how you end up with this. These electrons bond with that carbon right there, and you get this neutral thing. Okay, so to finish her off, let's learn a little vocabulary real quick. What we've just learned, whether we know it or not, is one of the most important concepts in organic chemistry. Where electrophiles, electro meaning electron, phile meaning love, electrophiles love electrons. These are going to be the things that are more positively charged, like if you have a partial positive or a full-on positive. Okay. Bases are nucleophiles. In order for it to be a nucleophile, it must either have a partial negative, have a lone pair, have a double bond, have a triple bond, or a full negative. But if it has a full negative, it's got a lone pair. So it says draw the products of each reaction, etc. Okay, so, and label the nucleophile and electrophile. So when looking at these two things, a nucleophile is a thing that has a lone pair, double bond, triple bond. This one has a lone pair, double bond, or triple bond. This is the nucleophile. This is the electrophile for the same reason we just discussed, that if you have, I'm going to draw it again. Let's pretend that doesn't exist. For the same reason we talked about before, which is that you have a boron with 3 bromines around it. We know bromines are decently electronegative, causing this to have a partial positive charge in it. And these electrons right here seek it out like that. Okay. And they seek it out, and then all you have to do, what I suggest you guys do, is redraw the one that looks the most complex to you. Usually that's the organic part. So if this is our arrow, we're going to redraw it. We have the oxygen like this. We had those 2 dots down there. But these 2 dots came up and joined a bromine. And on that bromine, boron, sorry, I don't know what, I've been talking for at least 8 hours straight. So on that oxygen is a boron, and on that boron is 3 bromines. And now all we have to do is look at the charge. The boron was totally happy before, and now it's gained a charge, so now that boron is negative. And this oxygen had a 0 formal charge, and now it's lost an electron, so it's positive. All right, feel free to pause the video and do this one. But I'm going to do it. Actually, I don't think I need to redraw that whole thing. We'll do Al, and we'll put Cl3 on it. So you have an aluminum, and you have 3 chlorines pulling the electron density away from the aluminum, giving the aluminum a partial positive charge, which we don't have to write. I do that just to indicate that it's got partial positive. And then here we have a lone pair of electrons. So this is the nucleophile. This is the electrophile. And what this is going to do, because I redrew it down here, I'll just scribble it out. These lone pairs are going to attack that aluminum. For our product, you want to redraw the more complicated part just the way it is, so you don't have to think about it. You even have those two dots just the way they are. And then we know that it attached to aluminum, and that aluminum had 3 chlorines on it. We know that the aluminum gained an electron when it bonded, making it negative. And we know that the oxygen lost an electron bonding with the chloride, bonding with the aluminum, making it positive. Whew. And that's that. Did it. You did it. Have a great day.